Guys, so we're gonna pick up where we left off in the last video. Uh, I just want to point out one thing before we start. I hope you remember this code here. We tried this one in the last video. If you tried this code in your home, I'm expecting you might notice that every time you run the code, it gives you different addresses. And that's only because you're running on Windows. If you're running, if this is the code you burn on a microcontroller, and it's bare metal microcontroller, you're not using any operating system or any complex operating system like Windows. The only thing that will define these addresses is the sequence of function calls you do and where you initialize your stack pointer using your startup code. But in the case of Windows allocate your program in different places with a special stack, not like a typical microcontroller. Okay, so in this video we're gonna talk more about the operations, the simple operations of the pointers, and we'll go a little bit into the array, the pointer to array and how it is used, and the pointer to structs and user defined data types. Okay, uh, so I hope you remember this code. If you don't, you can go back to the previous video and remember it well, because we're gonna work similar stuff. So I guess we don't need this part here. So let's get to something we talked about in the last video and see how it is. So this is the size of the pointer itself, not the value it points to, not the variable it points to, it's the size of the pointer. So here is its 4. So 4 meaning it's 4 bytes because it's 32-bit system. Okay? However, if we say like size of let's say your character z equals a, and we say size of z, that should be 1 on this microcontroller or on this system or any other system. Okay, so it's 1 because character is always 1 byte, it's ASCII. Okay, so let's get back to last time's example, like this one here. So I'm gonna copy paste, but copy paste is not the best practice, so don't try it. Okay, so let's see how things change through the steps. Okay, so we're gonna no, this is not necessary. Okay, so here we need we want to print this. And again, I'm gonna repeat a little bit on this part. When you type asterisk y, basically you're dereferencing y, meaning you get the value that y points to, which at this point is it should print 100 because we got the address using this operator here. We got the address of x and put it into y as a pointer. Then we got y as a pointer, which points to x because it has the address of x. We can print that too to look at it. Okay, so we can print so we can print everything mostly, so it looks familiar. So let's say and here we hit equals, and let's type the address or the pointer as we say. Okay, and here we're not gonna print size of z, we're gonna print, okay, that should be good, which would print y. Now it should be pointing to z. So and here we're gonna, okay, we're gonna use this one. At this point, dereferencing y should get us 2000, not 100, because at this step here we made y point to z instead of x. And again, also I repeat from the last video, we didn't use asterisk y because here the compiler already know y is pointer, so I need only to use asterisk to declare a pointer or define a pointer, but not to use it as a pointer elsewhere in the code. Okay, so let's run this and see what we get. So does it look right? Yes, it looks much right. So here we get dereferencing y is where y points, the value where y points, which is 100. And the address where y points is this address, which is the address of x. Wow. And then the address of z and where y points, those are here, and they are the same because after this step in line 11 y points to z, so they have the same address. And when we dereference y, since it points to z, which is actually obvious, it gives us 2000, which is the value that z holds. Okay, that's about right. Okay, so we don't want that anymore. So let's try this trick here we used, where we said that if we do that, the value of z will change. So how about we try this? So we don't, at this point we don't want the address of z because we already printed it, and the stack doesn't change by itself as long as it didn't call another function. So this should look right. Okay, so again we will run it, and okay, so the first three parts are the same. Y still, the value that y points to is 100. Y points to this address, which is the address of x, and here is the address of z, and y points to the address of z. We're talking about this part here. Okay, and when we dereference y here, it gives us 2000. But the new part is z. Wow, z changed without we changing z. How did that happen? Because, like we talked about in the last video, y actually points to where, or has the address where z is saved in the stack or in the memory. So when you change it, you actually, when you change the value where y points using the dereferencing of y and equating it to another value, this value is put where y points, which is in this case z. So it's 1, 2, 3, and again y still points to the same last address, which is the address of z. Okay, so That's pretty much the tips and tricks of the basic operations of pointers. We can try one last one, uh, if you want, and if you don't want, I'll still do it anyway. Uh, so we don't want all of that again, right? Okay, so let's say at this point we say z equals the dereferencing of y, and here we print z. What are you expecting the value of z? Would it be 100 or would it be 2000? I say it would be, yes, I'm hearing someone say 2000. It's wrong. It's gonna be 100. So let's see. Wow, it's 100. How did that happen? Again, when you dereference the pointer, you get the value where that pointer points. And in this new code we're using now, y actually points to x, and the value that x or dereferencing y holds is 100. So this here is equivalent to z equals x, which is simple programming, nothing serious. Okay, so let's get into something a little bit more complex. A little bit into pointers and user-defined types, because we're gonna use that a lot in the next video or videos, however it goes. Okay, so let's say so here I'm actually creating an array of 10 elements and initializing all the elements to zeros, because as you probably know, the stack is not initialized, so it would be initialized to rubbish unless I manually initialize it like here, or like explicitly initialized. Okay, so let's try something out. If we say here, okay, that's a bit tricky. So when we define or declare an array, the name of the array is actually a pointer, or more like the address of the first element in the array. So we're gonna see this here. So we're gonna print out array, which is just the name, not an element. Like I said, it should be the pointer to the first array, the first element in the array, and let's say here pointer to array of 0, and we use this operator here to get its address again. And again we're gonna write that down. So what are you expecting? So if you're a bit familiar with programming, you probably know that array of 0 or ar of 0, like we're writing it here, this should give you the first element in the array, which is just an element in the array. And since it's an array of integers, this should be just like x or z, it's just another integer. So when we use this operator here to get its address, we should get the address of the first element in the array. And if I was right and r here is actually a pointer or the address of the first element, those two should print here exactly the same value. Okay, so let's not use this for now. Okay, so let's print this out here. Wow, I was right. I told you I would be right. They are actually the same value, because r is a pointer to the first element. Uh, that's a note for later, but it still works. When we say r is pointer to the first element, yes, it is a pointer, but it's not a pointer like y. It is a constant pointer to variable data. We'll get into this part in later videos. Don't bother about it now. But that's why if you try to say r equal and z, you'll get a syntax error, or not syntax error, you'll get a compilation error basically. I'm sorry for this mistake, because it is a constant pointer to variable data, meaning when you have r is a pointer that points to a fixed location in the memory. You can't change where it points, but you can change the data it points to. Okay? Okay. Uh, we'll get back to this part in later videos. So if you're not getting it now, we'll get back to it. So let's try something else, okay? So if we say here array of 1, so what are we expecting? We're expecting that this address here will be after this address by 4, because in 32-bit systems the integer takes 4 bytes, so this and this should have 4-byte difference. Let's try this out, okay? Oh, they have 4 bytes difference. I was right. So what does this mean? This means that this operator here works even on the elements of the array, each element as if it's a total separate integer like x or z. So what's the size of array? That's a bit tricky. Can you guess? Can you guess? I'm listening to someone saying it's 4. Is it 4? Is it? I don't know. Let's find out together, okay? Oh, it's 40, not 4. So this is basically because it's statically allocated array, so it's not actually a typical pointer. So it knows the full size of the array, and when you do that, you get the full size of the array. That's a bit tricky, but it's useful. We might get back to where it's useful later. So the last thing we're gonna talk about in this video is user-defined data types. Let's say here what? We have 10 character names? That's so short. Still is good, okay. We need to type in my struct. That's so messy name, don't try this at home, because it's so bad. But I like to do bad stuff. Okay, so what do we need here? Do we need all this? No, we don't. Okay, so if we say my struct m, so do you think I can do? Oh, it didn't give a syntax mistake. Is it? Can I do that? I guess I actually can. So if we say, will it work? Do you think it will work? Yes, I think it will. Because it's actually right. Or probably. So, if we say here, so I'm a narcissist and I like to use my name a lot. So, assuming that we did this here, so this is my name, Mina. I am Mina, okay. So we use this and we say like I equals 11. Can we do that? Yes, I guess we can. So if after using this part here, we got the address of M where M is stored, and we got this address and put it into PTR. So how we use this now we're gonna get to another operator that we use, and let's say I equals 12, not 11. Look at that. So if we get here and we say m dot I, and m dot I is an integer, so what's gonna happen now? Is it gonna print 11 or 12? So let's check. Wow, it printed 12. So here the arrow operator is used when you use a pointer to point to a user-defined data type. So to access the elements of that user-defined data type by a pointer to it, not by its instance, use the arrow operator. So the arrow operator works to dereference a member. I want to get this simple, so okay, so let's do this again. Okay, so I here declared m as an instance of type myStruct, which is looks like this, and then I made ptr, which is a pointer to that points to the same type, my defined data type, which is myStruct. And then I got the address of m and put it in ptr. So now ptr points to the instance I created here. So to dereference the elements, in m, we use the arrow operator. So ptr points to m, and when we use the arrow operator we can directly access the members of m, which in our case is a character array, and I, which is just an integer. Okay, so let's try this again. Okay, so what if I'm called Nina? Nah, that would be so awful, but still works. So let's try it. Nina. Oh, that's so bad. Oh, 78, I'm sorry. We should have typed it as a character. Oh, typed N, not M. Because we actually dereferenced that. So that's a multiple level here, because that points to struct, which points to M, and so we dereference it to get the array and then access the first element in the array and change it. Now I know it may be a bit complicated, but it works just fine, so don't worry, we're gonna make so much more examples in the next videos. If you have any question, please leave a comment. If you have any request, please leave a comment. And if we ever worked with the complex code, I'm gonna give you a link to its GitHub. so don't worry. Thank you for watching. Thank you.